Hello everyone, last time I gave you this problem about a self-describing number. The idea was we have a 10-digit number such that the first digit tells me how many zeros there are in the number. The second digit will tell me how many ones there are in the number, and the 10th digit tells me how many nines there are in the number. And I asked you to work out what the number was. Now, this wasn't a very difficult problem, I know, and a lot of you were very successful with it. I think almost everyone got the answer, and so the answer was, there we go, so I think that is 6,210,000,000 or 621,000,1000. So I know a lot of people got this. One of the people who attempted this problem was fellow internet maths person, Mr. Matt Parker, who, by the way, is there! Look at him!
Yeah, I heard James was making a video where he held up a picture of me, making a video where I held up a picture of him. So, like James said, I did have a go at the puzzle as well, and I'm quite proud I got the solution.
High five!
Thank you very much.
And so we're going to talk about the different ways people got the answer to this problem.
So I seem to do what most people in my comments and your comments did, which was I looked at it and went, you know what, it's going to be largely zeros. And so I had a best guess, and then I kind of iterated fixes on that until I got to the solution.
Yeah, that's what I saw people doing. So people made their best guess was tended to be something like the 9 billion with the 9 at the start.
Yeah, I thought lots of zeros, one big number. And then I went, there's going to be a few other small ones just to
it doesn't
balance
quite work.
I'll move that across one, I'll change that. Yeah,
I haven't counted the 9, so I need a 1 somewhere in there. If I put a 1 in there, then that has to be adjusted. And so small fixes, and step by step, they got to the correct answer.
Thank you.
There is no suggestion of how hard this problem is going to be from the statement of the
phrasing gives away nothing about how
because
complicated
potentially there are, 9 billion...
It could be...
numbers to check.
Yeah.
So it could be a really difficult problem. It turns out it wasn't such a difficult problem, but we don't know that just from knowing nothing at all.
You never know when you start.
So I know that some people attempted a more mathematical solution. So let's take a look at this. So what some people did is that they noticed that the sum of the digits add up to 10.
I noticed that as well for the record.
So why do the sum of the digits add up to 10? Because the values in the number are tallies. They're tallies of how many ones you have, how many twos you have, how many zeros.
And you're counting 10 things, so the total is 10.
If you add up the tallies, you should get 10, right? So it should all add up to 10, which means the number we're looking for, whatever it is, should be a partition of 10.
Also, it's numbers that add to 10. So a partition is like 7 and 3, or 6 and 3 and 1, or something.
So this is how I solved this. This is how I solved it.
Oh, nice.
So my natural instinct was to go a bit more mathsy. Sorry about that, Matt. And so I went for this. Partitions of 10. There are 42 partitions of 10.
To be fair, because I found my solution, but I wasn't thorough enough to know if there were other solutions I'd missed or anything.
This is what I wanted to do.
Yeah.
So, and I noticed other people in the comments wanted to know when they found a solution, which they did.
Are there more?
Are there more? Is it a unique solution?
Good question.
And that's what I wanted to know as well. So I went through the 42 possible partitions of 10. Just checked if they worked. In fact, I was checking if it described itself. I noticed the number, whatever it is, would have to describe itself as well. So it was something that was stable under that idea. So checking all 42 partitions got me the answer, and it told me it was the only answer.
And can you prove that?
I can prove that if I have something to lean on. So what I want to show you is a proof which shows you what the self-describing numbers are, and it tells you actually all the self-describing numbers. I didn't come up with this proof, so the way I did it wasn't as good as this, but this is what we're going to do. So we're going to have an n-digit number. So it's not just a 10-digit number, it could be anything. So let's call it A0, A1, A2, and so on up to n-1. All right, so that's our n-digit number. Now here's something to notice. The first one digit here, the A0 is going to be greater than 0. It can't be 0 itself because that's kind of self-contradictory, so kind of a bit of a paradox.
That makes sense.
There we go. Don't build up your parts. So A0 has to be bigger than 0. Out of the remaining digits here, let's say there are non-zero values, okay? Now, what I want to do is tally up how many non-zero values I have. So let's do a tally of total number of non-zero values. So there's two ways of looking at this. We could just count up all the 1 digits, all the 2 digits, all the 3 digits, which means this is equal to the tally of the 1 digits plus the tally for the 2 digits and the 3 digits and so on. Or we could count up how many non-zero values there are. Well, I've already said there's P here, and there's actually one more at the beginning. All right. So altogether there's P plus 1 non-zero values. So what does this mean? It means we have P non-zero values adding to P plus 1. That's enough to tell us that most of these digits are going to be 1s or maybe a 2, mostly zeros, except for perhaps the A0 digit at the beginning. So A0 at the beginning, that could be bigger than 2. If it is, then this is what you're going to get. You're going to get something like J, 2, 1, lots of zeros. You'll get a 1 here in the jth place, or counting the J, and then 3 more zeros at the end. All right, so they all look like that. The solutions all look like that. So we would have solutions like 3, 2, 1, 1, 0, 0, 0. We would have 4, 2, 1, 0, 1, 0, 0, 0, 5, 2, 1, 0, 0, 1, 0, 0, 0, and 6, 2, 1, 0, 0, 0, 1, 0, 0, 0. Right, that's what you're going to get. If this number is less than 2, that actually restricts how long the digit can be, or how long the digits of the number can be. You're going to get short numbers. You're going to get a few exceptional cases, actually 3 of them, and they are 1, 2, 1, 0, 2, 0, 2, 0, and 2, 1, 2, 0, 0, and that is a complete list of every self-describing number. That's the mathematical proof. I know, however, some people did the same sort of thing, but they used a computer program.
And that was actually my thought, because I was nowhere near as rigorous as James. Once I had evolved my one solution, I wondered, are there any more? And so my first response then was to think I could write a computer program to find that, which a lot of other people did.
It's not proper maths.
It's totally proper maths. I mean, I love coding. Thank you, everyone who pasted all of your code into the comments on YouTube. It looks hugely suspicious, but I've got reams of code across at least 3 different languages. And I think there is a place for programming in mathematics, because solving a puzzle like you did is good.
It's brute force.
You're on the ground, you're hacking through the mathematical jungle, you're finding a path.
Checking.
No.
Where's the insight?
No, programming.
Where's the mathematical learning from that?
If you're too close to the jungle and you're making progress and you're finding things, programming is like getting in a helicopter, flying up and seeing all of the local terrain. You might go, oh look, there's an interesting thing over there. I'm going to go back down and go in that direction.
Are there infinitely many?
No, you can't prove things unless you're exhausted, but you can. I think you can find some fantastic insights. And fellow internet maths person Katie Steckles wrote a program that came up with some fantastic results. And she's here.
Hi guys, I heard you were doing a video where you hold up screenshots from the same video.
So, Katie, what did your program do?
Okay, so, I guess there's probably a few ways you could write a program to attack this problem. The one I went with was that I wrote a program which takes in as an input a 10-digit number.
Right.
And it spits out the tallies for that number. So it tells you how many zeros, how many ones, and so on.
Okay, so this is the counting for you.
Yeah.
Okay, I saw a few people did this, and then they ran it across every possible 10-digit number.
Yeah, I may have done that.
That.
Yeah, that's pretty much what I did. And what I was looking for with this program was a number which, when I feed that number in, I get the same number out.
Oh, so it doesn't change when it goes through that program?
Yeah, it kind of it's a fixed point.
Similar to what I was trying. So I wrote out the 42 partitions of 10, and I was looking for a fixed point.
Yeah, essentially. And what I found was that when you put in all of the 9 billion possible numbers, all of them immediately go to one of those partitions of 10, because it
so they all go down to
gives you a tally.
42, of course.
Yeah.
Right.
So that's the first step that happens.
So what happened with these 42 partitions?
Well, essentially, when you put them into the program, they fell into 2 types. Okay, there were two different things that happened. And again, I mean, it would probably be easiest if I had something to lean on.
So explain to us what's going on here.
Okay, so one of the things that can happen to your number is that it goes to one of these 9 partitions. And these 9 partitions all take you to the correct answer. So you can see the first one here is 6, 2 and 2 1s, and that is the setup that you have in the
So if you apply this counting function on it, this counting algorithm on it, you're going to get back to 6211.
Yeah, it may not go straight there. It might go to one of the others first, but eventually these will all end up at 6211.
So if we took another different one here, if we took this one here, the 3, 2, 1, 1, 1, 1, 1. So this is a partition of 10 without the zeros on it.
Yep.
So if we apply the counting idea onto it, I think we would get there's 3 zeros there as well, 5 1s, one of each of those, so that would take us to this partition.
Yep.
5 3 1 1, and then you just keep applying that algorithm.
Yeah, and these ones will all end up at the correct solution
Eventually. Hooray. But what else did you find?
Well, there was one other thing that could happen, and in fact, I'm a lefty, so
Right.
let's do a thing. Okay, so what would the other thing that would happen is that you would end up at one of 2 places, and that's either this number, which is 7 1 0 1 0 1 0 0 0. So that's 7 zeros, 1 1 0 2s, 1 3 0 3s, 1 4 5,
And 0 the rest.
and 0 for the rest.
Yeah, exactly.
Or you would end up at this number, which is 6 3 0 0 0 0 0 1 0 0. But what's interesting is that if you go to this number and apply the counting function to this number, you get this one. And if you apply the counting function to this number, you get that one. So they're kind of like
Lovely.
friends. They're counting friends.
Yeah, it's like perfect numbers. Well, this would be the perfect number because it gets back to itself.
Yep.
And this would be like amicable numbers. They're kind of
Yeah.
a pair. They
Yeah.
describe each other.
So you kind of end up trapped in this loop, just flipping between those two.
That is lovely.
And this is the thing,
I
because
don't know how I feel
programming,
being trapped. Yeah.
programming has let me kind of see this landscape and see what happens to all these different numbers, and I love it.
So that's, I guess, all we have to say about this problem. I think we've exhausted everything.
There are a few fringe cases. People who solved it by looking it up online. People who checked the online encyclopedia of integer sequences. That is a good method. People who then just posted that in the comments on the videos.
People just looked at the comments.
Yeah, people read the other comments.
People who write 42 for every question.
And happened to be right this time. Yeah, and I bet these are all valid methods, but for me, they're things you do when you get bored of exploring it yourself.
But I think that is all we have to say about this. So I'll just say thank you to Katie Steckles. And if you want to see Katie's videos, you should click in this area here. If you want to see Matt Parker's videos, click around this area. And from me, if you have been, thanks for watching.